Hey guys, so welcome to part 2 of our lessons about covalent bonding. So today we're going to talk about molecular shapes. Awesome. We are going to describe how VSEPR theory explains molecular shapes. VSEPR stands for valence shell electron pair repulsion. And we're going to learn about the 5 basic shapes that we need to know for class. So basically, molecules form their shapes based on VSEPR theory. So here you can see what VSEPR means, valence shell electron pair repulsion. It literally is when electrons from adjacent atoms are repelling each other because electrons are negative and a negative will repel each other, just like if you stuck two ends of the same poles of a magnet together, like two negative ends, they're going to repel each other. The atoms will do the same thing because of their electron valence shells. Here are a bunch of different shapes. We're only going to do the first 5. If you take AP Chem or College Chem, you'll learn about these other ones. But for our purposes, we're going to learn about linear, the triganol planar shape, bent, pyramidal, and the tetrahedral. Just don't worry about the rest of them. But there's what they look like. These are called stick and ball models. The balls represent atoms, and the sticks represent the bonds between them. And remember, a covalent bond is when 2 electrons are shared between 2 atoms. All right, so the first shape we'll look at is something called linear. These are going to be in the shape of a straight line. So anytime you have 2 atoms, the shape will always be linear. For example, say you have H2. We're going to do the dot structure for this. Just H's next to each other. We don't need any lone pairs. We have 2 atoms. That's it. That's a linear atom. How about if we have something like HBr? Again, if we did the Lewis dot structure for this, we'd have H, we'd have Br, and then we would have some unshared pairs on the Br. But again, it's just a molecule with a straight line across. They just go right next to each other. You can also have a linear molecule with 3 atoms. Let's take CO2, for example. If we did the Lewis dot structure for this, it would look like this. We have C, we have a couple double bonds here with the O's, and we have some unshared pairs on the O's. Okay, here's 3 atoms. This is going to be a linear molecule. It's just going to go straight across, all in the same plane. One of the keys here, though, is to realize that the carbon has 0 unshared pairs. That's what makes this a linear molecule. So whenever you have 3 atoms with 0 unshared pairs, you're going to have a linear molecule. The next shape is called bent. This will also have 3 atoms in it. Let's take water, for example, H2O. And if we did the Lewis structure for water, it would look like this. And I'm going to kind of draw it now and how a bent molecule would be. Okay, so this time we have 3 atoms, but now we have a couple unshared pairs on the central atom. So this is the rule for bent molecules. If you have 1 or 2 lone pairs, unshared pairs, on the central atom, it has to be on the middle one. The ones on the ends don't really count here. We have to focus on the middle because remember what VSEPR means, valence shell electron pair repulsion. These electrons, these unshared electrons on the oxygen are going to literally push down on the hydrogens because these electrons here are repelling the electrons that are around the hydrogen, forcing them downward, just like if you had a magnet with the same poles try and put together, they're going to repel each other. So this is why it takes on this bent shape. Very important. So the criteria for bent is you have to have 3 atoms and 1 or 2 lone pairs on the central atom. That's how it's different from the linear molecule where we had CO2, which was like this. We have unshared pairs on the O's, but that doesn't count. There's no unshared pairs on the carbon, so this one is bent and this one is linear. Okay, the next shape is called triganal planar. This time we're up to 4 total atoms. All right, so as you can see, one of the ways to figure out the shapes of molecules is how many atoms they have. We're just going to either do 2, 3, 4, or 5. That's it. We're staying to simple atoms. So for trigonal planar ones, if you have 4 atoms, so an example for that would be, let's do SO3. If we did the dot structure for this, it's going to look like this. We're going to have some O's here. We're going to attach it to the central atom, to the sulfurs. We're going to need a double bond in here. I'm not going to go through how to do this again. I did that in the last video. So if you know how to do the structure, go watch that. So it's going to look like this. So we have 4 atoms, 1, 2, 3, 4, and we have 0 lone pairs on the central atom. Remember, it's about the central atom. We don't really care about the ones on the end. So this is going to be a flat molecule where the O's are symmetrically around the sulfur on the same plane. So this is really important when we start talking about polarity in the next video. So here's your next one, this trigonal planar, and the criteria for that is 4 atoms with 0 lone pairs on the central atom. Let's take a look at the next shape, which is also going to have 4 atoms, but as you may be thinking, it has to do with the lone pairs on the middle, because this is about VSEPR, valence shell electron pair repulsion. There's no electrons here on the central atom, so it's not going to push the oxygens down, so they're just going to all be around it nice and evenly on the same plane. Okay, the next shape is called a pyramidal, kind of like a pyramid because it takes on a pyramid kind of shape. So this one also has 4 atoms total, but this time we have 1 or 2 lone pairs on the central atom. So as you can see, it has to do with what's going on the central atom as far as lone pairs go. So here's a good example, classic example of a pyramidal. We have ammonia, NH3. Okay, the dot structure for this is going to be this. And notice how I'm drawing this and how it's different from this SO3 we just did a second ago. I'm putting the H's downward because I know this is going to be a pyramid. If you're drawing these, you're drawing the structures, and you don't draw it in the shape right away because you have to actually draw the shape to figure out what it's going to be, because it depends on if there's lone pairs on the central atom or not. So you don't know if this is going to have lone pairs here unless you actually do it. Okay, so we have the lone pairs. We have the 4 atoms. These electrons, again, are repelling these H's downward. Down, so it takes on this pyramid shape with a point at the top. Again, very much different than the SO3 we did a second ago. Has to do with the lone pairs repelling the atoms down. And finally, the last one is the easiest one of them all. This is the only one that has 5 atoms. You don't have to worry about lone pairs because they're all just going to take on the shape. Let's look at the CH4. We kind of looked at that before. We have a C in the middle, and I'm going to put the H's around like this because this takes on the classic tetrahedral shape. So whenever you have 5 atoms, 1, 2, 3, 4, 5, it's always going to be a tetrahedral. Notice there's no unshared on the carbons, and you're really probably not going to get unshared pairs for tetrahedrals anyway. So there you go. There's our 5th shape. Okay, so let's take a look at these shapes again and how they look in the stick and ball model. Here would be the linear one, something like CO2 with the C in the middle, the O's on the end, no unshared electrons here. This is different from the bent one that also has 3 atoms, but the bents will have unshared pairs on the central atom. right up here. The trigonal planar and the pyramidal are related because these both have 4 atoms. Okay, and the difference here is the central atom. The pyramidal is going to have 2 unshared pairs right here on the central atom, where the trigonal planar will not. Notice the difference. These unshared pairs that are here are bending down these other atoms, repelling them, repulsion. This trigonal planar one does not have unshared pairs, so there's no repulsion, so these atoms are simply going to be as far away as possible from the other ones. Here's the tetrahedral, 5 atoms total. We don't have to worry about unshared pairs, but they're all going to be in this shape. All right, so finally, here is a nice little summary table for you of the 5 shapes and the criteria for each. Notice the patterns that are involved here. So all you have to do is first count up how many atoms there are, see if there are lone pairs on the central atom. That's going to tell you what shape it's going to be. So this kind of shows you what I was talking about when I said that all the shapes are kind of based off the tetrahedral. We start on the left with methane. That's a classic tetrahedral molecule with a carbon in the middle, and the white balls are the hydrogens. But then look at ammonia, which would be a pyramidal shape. Look how it kind of looks like a tetrahedral. But instead of having that 4th atom on the left, it has an unshared pair. But it's in the same position as if there was another atom, because again, electrons are repelling each other in these atoms that are attached to the central atom. So they end up being as far away as possible. Look at the next one, water. That's a bent shape molecule. And again, look at where the lone pairs are, the unshared pairs, the blue dots. They are where atoms would be if there were atoms there. So again, it kind of looks like a tetrahedral if you imagine those unshared pairs were atoms. And then the last one is just simply hydrogen fluoride, just HF stuck together. But remember that F is going to have 3 pairs of unshared paired electrons, the blue dots, and again, those would be where an attached atom would be. So again, the entire thing with the unshared pair of electrons takes on a tetrahedral type of shape.